Um, no, it should be working. So good morning, everyone. So today we will be going into so we kind of start with an introduction, talking about earthquakes in general, how we quantify the hazard, how do we describe the intensity of the shaking, and how do we predict it. So now we will start to try to combine all of them in order to be able to evaluate the hazard from seismic sources. So there will be a little bit of repeat and going to further detail on what we discussed, as well as seeing new things. As always, we can start maybe with a review of some of the key material from the last time. So, who can tell me the way that we categorize the ground motion parameters, which are the three big groups that we defined? Yes, Chris.
Intensity, duration,
And
and
anyone else? The frequency content. Exactly. Yes. And some of the parameters describe like either one of these groups alone or maybe a combination. For example, spectral accelerations define the intensity, but over only a narrow frequency content. Thank you. So for the intensity parameters, can anyone give me some examples of them? Areas intensity is one. Yes. Another? Exactly. Yes. And how would you define those?
peak, peak of
Yeah.
massing acceleration.
Exactly. Yes. Um, some parameter we said that like spectral acceleration, Fourier amplitude spectra. And now to predict them, what are the two components that a ground motion model needs to include to to be able to give us information about?
Like the two types of uncertainty.
That's how we separate the uncertainty, but with uncertainty alone, can we make a prediction? What else do we need?
Distance, soil connectiveness.
Yes. So we need all of these. And what do these parameters give us in addition to define the uncertainty?
Maybe the intensity measure.
The mean or like the average intensity, right? So you know the average, you know the uncertainty, and now you have the entire distribution. Exactly. Yeah, so it's the mean prediction and the variability. And then how like we describe like typically there are three processes that affect the mean of these intensity parameters. So can anyone tell me what these processes were? Like we start with the earthquake and we record it at the site. So what is happening in between? The attenuation. So the attenuation is related to what?
Soil
But the entire path. The rock type has to do with sort of the amplification. Yes. So we have sort of the site effects, which are like whether it's rock, whether it's soil, how soft the soil it is. The attenuation, as you described, which is essentially the effects of the path, so how the seismic waves change as they travel through the crust. And we also have the source, so how the seismic waves are generated at the fault. Any questions on that?
we covered into when you the ergodic and
Yes.
in brief.
I think, yes, we will go into more detail. I kind of wanted to give sort of a direction of where we are going. I think we will, in this lecture, we'll take a step back and kind of again build through that. But the general idea is real. So the difference between ergodic and non-ergodic model is how they describe these three effects. in an ergodic model, you assume that there is a global average relationship that gives you the source effects. Same thing with the path, same thing with the site. For the non-ergodic models, you recognize that all of these, the source, the path, and the sites, can be different from one location to another. So even that goes to first lecture or the second lecture, maybe where we saw the earthquake in Toronto and the one in California. Yeah. But we will go through the math maybe in two lectures. Okay. So now moving to the seismic hazard, the reason that we have this framework is because like when we design a building, we need to select an appropriate ground motion for that design. And so can anyone tell me what factors you may want to consider in deciding what is an appropriate ground motion value to use for your design?
The criticality of it, like criticality.
Correct. Yes. So how like and so if you can expand like the more important your structure is, then sort of the more conservative you want to be in how you select that parameter. So that's the structure itself. What about sort of the earthquake, like the source? So does it matter like whether we are in a region that has like very long faults and they can produce very large earthquakes, or we are in some region where the faults tend to be smaller and so you don't have these big earthquakes, or does the frequency of the earthquakes happen? So you can be in regions that historically, like you have earthquakes in New Madrid, but they may happen once every 300, 400 years versus you can have the same size earthquakes but happening every 50 years. So does the frequency of the event also matter? So those are the two things that different approaches take into consideration in coming up with an appropriate design level. And the two main groups of this analysis are the deterministic hazard analysis, which takes into consideration the size of the events and where these events are relative to your structure, because that's also important, right? It's not only that you have a magnitude 8, but some structure can be next to like the San Andreas Fault that will experience that magnitude 8 at very close distance, and some other structure may be 100 kilometers away. So the deterministic analysis will account for the size of the earthquake and where these earthquakes we are expect them to happen. And then we have the probabilistic method, which in addition to the size and the location, it also takes into account how frequent the different earthquakes can happen and how that affects our decision as to what is an appropriate design value. So we can go first through the deterministic analysis, and then some of these same things will be applicable to the probabilistic. So the first step is to define our site conditions. So this is where our site is located and some information about its geology. So like the VS30 parameter to quantify it and some other parameters that we will see next. After that, we can go and define all of the possible earthquake sources that are around our site, and that are all the sources that can contribute to potential earthquakes that our site may experience. And in this example here, we have three faults. We have identified fault one, and in identifying it, we need to know some information about its geometry, so where it's located, and what size of earthquakes it is capable of producing. For the deterministic analysis, when we try to define the earthquake size, typically we care about the maximum earthquake that fault is capable, or the characteristic earthquake size that this fault is capable of producing, and we will see how to do this calculation. We have a second fault that may be a little bit further away, and then we have a background zone, which again, we need to define both its geometry and what types of earthquakes it can produce. Then for each of these sources, we compute, like as you remember in the previous lecture, we defined the different distance metrics. So how do we define the distance between each fault and our site? And we saw a number of parameters. So now if we know the geometry of the faults and we also know where our site is located, then you simply apply these formulas and calculate these numbers. And then using a ground motion model, we can evaluate what is the ground motion that each of these sources is capable of producing. So here, let's assume that we have summarized information. We have the three faults, the characteristic magnitudes, that these faults can produce, the distances, and then based on that, we can plug a ground motion model to get the spectral acceleration for the fundamental period of the structure. And one thing to recognize, if you like going back again to the previous lecture, we don't get a single ground motion from each scenario. We get a distribution. So in the deterministic analysis, we need to make some choice ourselves as to what percentile we are going to select, whether it's going to be the median or the mean, or it may be some higher percentile. And that goes back to what you said about how important a structure is. Like, if it's an average important structure, then maybe the median is a good estimate. But if it's something that, like, if it's a hospital or if it's like a fire station, then you want to account for all the cases where an earthquake can happen and can produce above average ground motions. And okay, so we have all of this. Now, as an engineer, how would you select which spectral acceleration to use here? What would you consider? Like, let's say this is 0.2, this is 0.3, and this is 0.25. What would make you choose the average? We have the average that each of these faults is capable of producing, and the average that we can calculate between these faults, right? So when you say the average, you are referring to the average of a particular source or the average.
That's the case.
Yes, and you can think like there are even tinier faults that can produce tiny earthquakes. And so if you were to average across all of the potential sources, then that value can significantly decrease. So typically what you do is the first thing that you propose is that from all these possible scenarios, you take the maximum. And here, let's say that fault 2 produced the maximum ground motion. Yeah. Any questions maybe on the steps to run a deterministic hazard analysis? Yes.
The controlling scenario is the one that produces the largest ground motion.
Yes. The largest ground motion for a given percentile. So you can assume this choice may change depending on which percentile you choose. Let's say that fault 1, the average is like slightly less, but the variability around the average is higher. So if you go to a higher percentile, then that distribution is going to be wider, and so it may still create a larger ground motion. Yeah. Any other question? Yes, please.
So background zone is where the site is located.
The background zone can be covering the site. Here for like, yes, so that's sort of the next slide. That's a great. Can you see? So this is actually from a seismic hazard analysis that I performed a few years ago. So this is a site in Philippines. And here we have a number of faults, major faults that we have identified. And the circles are all the earthquakes that we have in our catalog, and they're color coded based on their depth. And the size of the circle is the size of the earthquake itself. So you can see a lot of the earthquakes, especially the big ones, will happen more or less where we have identified previous faults. But then you also have many earthquakes that happen like at some within quotes, random location, right? So for example, this earthquake. There may be a fault, there is a fault there to produce the earthquake, but we hadn't been able to identify it in advance. So to account for all the earthquakes that can happen anywhere where we don't have enough information to define a fault, we use background zones. And those zones can outside can be within one of these zones. And in that case, like if you were to if you were to go to the, like compute the distance and your site is above your background zone, then maybe you will select some very small distance, or you can have a background zone that is like, I don't know, this zone that is further away. So is this helping with your question or no? Okay. And so, yeah, as we said, like the background zones are used to account for earthquakes where we haven't mapped previous faults. And one thing to recognize is that this typically depends on how well we know a particular area. So if we are in California where we have many earthquakes and a lot of research to identify faults, typically we don't have that many earthquakes in background zones. But the more you go to like offshore areas or areas that we don't really know the seismicity, then most of the earthquakes are explained by the background zones. And on average, the maximum earthquake that background zones can produce is smaller than the one that actual faults can, because if you have a very large earthquake, typically there is geologic evidence, and so you can identify the fault. Yeah, so the relationship between sort of the knowledge of a region and how much you will rely on background zones, as I said, depends on the area. So this was another project that I was involved, and this was like an offshore site. So you see, we have identified some faults, but almost none of the earthquakes are actually happening on these pre-mapped faults. So in the end, everything was explained with background seismicity. Any questions on the needs and the usefulness of background zones versus faults?
Could you explain background
Yes. Uh, Anything specific or go again?
zone? You have an earthquake, this is just the surrounding area that's not in the background zone, I'm confused as to what exactly it is.
So you have this polygon, for example, and you have all of the earthquakes that happen in here. So what we are saying is that these earthquakes can uniformly and randomly happen anywhere around this zone.
Okay.
Yes. And you do that because you don't know where the faults are located. So if you don't know where something exists, then you need to assign some distribution around it, and the most natural thing to do is to have a uniform distribution. So like the earthquake can be anywhere. Now for the deterministic analysis, we assumed like the closest distance if you go to the previous example. So like in this case, like the distance between the edge of the background zone and outside. So if you were to perform a deterministic evaluation here, for this background zone, your distance will be maybe from here to here, sort of the closest. Is this helping with the question or? Okay. And so this is even when we will see how to run a probabilistic seismic hazard calculation, this is sort of a back of the envelope calculation that always is good practice to perform to get a sense of the values that you should expect and whether they make sense or not. Okay, so if we and actually we can go through an example of like performing a deterministic analysis. So if I stop sharing, okay. So I think on UB Learns, I created this tools folder, and here is a spreadsheet with like some ground motion models that you can easily evaluate. So we can use those to run like a deterministic analysis. So in our case, we have these three sources with a magnitude 7.5, 6.86, and these distances that we have computed. So if you open that spreadsheet, so the way that it works, how big is it? So here you have your different ground motion models and how you will assign weights to them. So if you want, you can use only one of them and assign a weight of one, or you can say, I don't know which of them is true, so I assign equal weights. And then here you can provide all the information about like the magnitude, the distance metrics, the VS30, and all of the other terms. And it will give you the mean estimate and the plus or minus one standard deviation for all the structural periods. So in our example, the first source is a 7.5 earthquake, and it's at 20 kilometers away. And I think we use a VS30 of 500 meters per second. So let's say that our structure has a fundamental period of 0.5 seconds. So in that case, the median ground motion would be 0.36 G, or if we were to go to plus one standard deviation, it would have been 0.7. So here it will be 0.36. Now for the second one, we have a 6.8, and that's at 15 kilometers away. And for the same period, that's a 0.33 Gs. And then for the background zone, that's a magnitude 6, that is 10 kilometers away. And so here it will be 0.27. So in this case, then we would have said this is the design ground motion, the largest one that comes from fault one. Now, to motivate why this is good, but maybe not sufficient to make this decision, let's think how does the recurrence of these earthquakes affect our decision? So if we have the same sources, but now we know that this one happens once every 500 years. This happens once every 100 years, and this earthquake happens once every 40 years. And this is sort of the mean ground motion that they will produce, and this is the plus one standard deviation. Does that change? And let's say that we want to design a structure that has a 10% probability of collapse in 50 years. So the return period for which we want to design is around 500 years. So most likely within that range, it may experience this earthquake once, but it may experience this earthquake 5 times, and this earthquake 12 times. So one out of these 5 times can be a ground motion that will be above the mean, and same with this, with an even higher likelihood. So the probabilistic seismic hazard, which is sort of the more complete version, is taking into account the rate of the earthquakes in selecting sort of what percentile we should use. Any questions on the motivation? Okay, so then the way that probabilistic seismic hazard analysis works is more or less going through the same steps. So first defining the site location, then the sources, but then we need to have a model for each source that gives us the size and the rate of all possible earthquakes that fault is able to produce. And this will be given by the magnitude recurrence relationship, and we saw the most simple one, the truncated exponential, I think, in the first lecture. Then for all the possible earthquakes that are capable to being produced in one source, we're going to consider the distribution of ground motion that can be generated. And then we will compute what is the probability that that earthquake on that particular fault can produce a ground motion that will exceed some certain threshold value. And that threshold value depends on the importance of the structure. So in a schematic form, we again have the different faults, but now we say an earthquake can happen everywhere. So we have some distribution that defines the location of the source relative to our site. Then we also have some model that tells us how many earthquakes per year we can have on each of these faults for different magnitudes. And for each of these magnitudes, what is the distribution of ground motion that we can get? And we combine all of them to get the hazard curve. So mathematically, this is the equation that we use. So, and here I want to make sure that it's absolutely clear. So if something is confusing, we can spend as much time as needed. So we define the hazard for a ground motion exceeding some value Z as the sum of the rate of all the possible scenarios times the probability that that particular scenario, defined by magnitude mi and distance ri, can produce a ground motion that will exceed that value Z. So first of all, is this clear why this equation essentially describes the process that we qualitatively went through before? Or are there any questions? So if this is clear, then this was for discrete magnitudes and distances. But when we have a fault and we allow the rupture to be located anywhere around the fault, then we have continuous distributions for magnitudes and distance. So if you were to consider that each of these faults can create a number of earthquakes, the way that we extend these relations is now we are summing over all the possible earthquakes that are above some minimum magnitude that are capable of being generated in a particular fault. And then we integrate over the probability density function for the magnitude that gives us the likelihood of different magnitude values. And for each of these magnitude values, we are multiplying it with the probability that for that magnitude and at that distance, the ground motion will exceed the value Z. And to go from here to here, essentially, if you were to use like infinitesimal small magnitude increments, the way that you will have calculated the rate for each of the possible magnitudes that we go through the integration is that the rate of each one of them is equal to the number of all earthquakes generated at this fault times the probability of that earthquake happening relative to the rest, which is given by the density function times dn. And if you also have some distribution about the distance of where the earthquake is within a fault, then we also have the probability density function for the distances. And now we have the double integration from minimum magnitude to maximum magnitude and from minimum distance to maximum. Okay, so this is maybe to check the understanding if you are saying everything is clear. And this is an equation that you will get if you do this in practice, and some people that necessarily doesn't understand the method will ask. So the question that I have commonly been asked is, many actual practicing engineers will say this approach looks wrong. And why does it look wrong is they don't understand, like, the question is, why do we need to sum over the different sources to compute the hazard? So why do we sum the rates and the probability that each of these earthquakes will produce a large enough ground motion? And in their mind, essentially what they think is that, does this mean that we assume that all of these earthquakes will happen at once and we are summing the ground motion? So let's say fault 1 will create 0.2 G, fault 2 will create 0.3 G, and then our site will experience 0.5 G. Obviously, this is wrong, but can anyone tell me instead our summation, what does it sum over?
With the relative likelihoods of it, like the probability that particular earthquake will happen.
Exactly, yes. And why do we do that?
I mean, if we are just taking one source and we are just relying on it, but if we are taking the distribution, then we are considering the probability or the uncertainty that it could happen at any of.
Yes. And does your structure care which of the earthquakes produce that ground motion, or does it care about the ground motion itself?
Okay, where it occurs.
Exactly. So it's exactly right. The reason that we sum over all possible scenarios is because we are summing the rates or the probabilities, and we are summing the probabilities because the earthquake that caused our structure to collapse is not what is important. Is that how large the ground motion was that can come from any of the earthquakes that can cause this. Any? Are there any questions on this, or is this clear? Okay. So now let's expand this term and see how we calculate this. So the probability of a ground motion exceeding some value z, given the conditional variables, like magnet distance maybe VS30, is simply the integral of the density function that we get from a ground motion model from that value z to plus infinity, because we assume that these distributions are unbounded. And that's also equivalent to integrating from maybe 0 here, because you cannot have a negative ground motion, from 0 to plus infinity, considering the likelihood of having each of these ground motions, but having an indicator function where you only sum the likelihood of the ground motions that exceed that value. So this I of SA greater than Z is 1 when this is true, and 0 when this is false. So here you will integrate over the entire density function, but only sum the part that is from Z to plus infinity. And because for most ground motion models, the density function that describes the variability of the shaking is a log normal distribution, the way that we do it is 1 minus the cumulative distribution of a standard normal distribution. So if you have any normal distribution and you take a value and subtract the mean and then divide by the standard deviation of that distribution, then you convert it to a standard normal distribution, and then you can use all of the tables that you probably have seen in introductory statistics courses to evaluate the probability of exceedance. And this parameter, so this normalization, is also what we will define as epsilon in hazard terms. And so if we calculate the equivalent epsilon, then for a standard normal distribution, we can calculate what is the cumulative percent. So for example, for 0 epsilon, it's the 50th percentile. For plus 1 standard deviation from epsilon of 1 is the 84th. And then the probability of exceedance is 1 minus the cumulative percentile. So if we were to integrate from plus infinity up to that value, then if that area is 84%, then this will be 16%. This will be 50, and at the 16th percentile, this area will be 84. And the most, like, again, for very quick back of the envelope calculations, the two epsilons and percentiles that you should associate are the 0 epsilon, which corresponds to the 50% of exceedance, and an epsilon of +1 that corresponds to a 16% of exceedance. Okay, so now let's see how we define the location of the source for the probabilistic seismic hazard. So what essentially we want to define is the location and the dimensions of the rupture and the size of the earthquake. So we have already seen this. So, and then for the dimensions, or maybe let me, the way that, so if you saw from the sketch in the beginning here, here, so we know the fault, but if you have an earthquake, if it's a small magnitude earthquake, its rupture will not cover the entire fault. So that rupture can be anywhere here. And all the possible locations that rupture can be will give us the distribution for the distance. So now we can systematically go on how do we describe the location of the rupture in order to define the distribution for the distance. So defining the distribution for the distance directly is not straightforward. So instead, what we will do is we will have some distributions about the area of the rupture and the width of the rupture, and that will give us the dimensions of the rupture itself in probabilistic terms. And then by knowing what is the fault plane and how big is our rupture, we can consider all the possible locations that rupture can be within the rupture plane, and that will give us the distributions for the location of the rupture along the strike of the fault, and the location of the rupture down deep on the fault plane.
So this fault plane is vertical, this is not planned, this is elevation.
It's not necessary, it can be tilted on a dip, like based on the dip of the fault, and then you will assume that the rupture is on that plane.
Okay.
You can also, I mean, there will be more things that you can consider, but then you can also add like a distribution for the dip of the fault plane if you assume that that's not well known, and that will further sort of broaden the distribution that defines the distance. But essentially, you need to consider all the uncertainties, all the randomness in the earthquake to come up with a probabilistic model for the distance. So first, for the rupture dimensions, there are a number of relationships that gives us for each magnitude the value for the mean value for the rupture area and the variability around that. So we can use the relationships like this to define the model for the area of the rupture. And then we can use either a model to define the width of the rupture. And as we said, as we even seen in, I think, lecture 2, this width can increase up to the point that essentially spans the entire grass. And that's why you will have, like, as the magnitude is increasing, the width is increasing, but then it reaches some constant value and it can increase even further. Or some other times you may want to model it based on its aspect ratio. So if you know the aspect ratio in the area, or if you know the width in the area, then you know all the dimensions of the rupture. You know its length, you know its width, and how this can vary. So now we assume that we have some value for the width and the length of the rupture itself. So now we need to decide how we are going to model how this rupture floats essentially within the fault plane. For the along stripe, so whether this box is located here or here or here, we assume typically that there is a uniform distribution because typically there is no preference of the earthquake to happen here on the fault plane versus here. Like if earthquakes didn't happen here or here, then simply the fault plane wouldn't have covered this region. But if this is the entire fault, then there is a more or less equal chance that the earthquake will locate it here, or anywhere along the stripe. And for the down dip distribution, most oftenly, we will also assume that there is a uniform distribution. So where the earthquake down dip the fault plane may occur is more or less equal. And that's not because necessarily that it's true, it's because this part doesn't really affect the final answer. So if it's not that important, then why add complexity? But if you see that it matters, then based on like previous seismicity, there is the observation that most hypocenters are located at some depth that is a few kilometers down from the surface. So there is like either a triangular or some type of trapezoidal distribution that tells you that earthquakes will not, on average, will not be concentrated uniformly along the depth, but at some, there will be some preference over some specific depth. And so you can model it with based on historical seismicity. Yes,
Is there,
please.
like soil type that would yield a trapezoidal distribution versus the triangular?
Trapezoidal versus triangular. The soil type, like, so this is kilometers. This is like 5 kilometers, 10 kilometers, 20 kilometers. If you define like soil strictly as like some loose material, that's only in the few hundred meters. And typically you will have earthquakes going through soil, but that part of the earthquake doesn't, because soil is soft, hasn't accumulated energy to release. So this distribution will be truncated, so will not cover the soil. But in terms of rock, if you were like another plot that maybe I can show next time is the stiffness, because of the overburden, the stiffness of the rock is increasing with depth and then starts decreasing again because as you go deeper and deeper, the heat is higher. So this is sort of the area with like more or less maximum stiffness. And so the one that releases that accumulates most of the energy and releases it, and that's why the earthquakes start here. Is this answering the question or okay? So now that we have the dimensions of the rupture, we need to define the size of the earthquake itself. And I believe we already seen the truncated exponential model maybe 2 lectures ago as like an introduction, so we can go now into more details. There are 4 main groups of magnitude recurrence models that you will see. The original one, the exponential, and then the truncated exponential that limits the size of the earthquake up to a maximum value. Then you have again, in the literature, these are not necessarily standard names. So there is like the characteristic magnitude model, or you will also see it as the Janssen-Compensmith maximum magnitude model. That's this red distribution, and that tells you that like all possible earthquakes can happen, let's say here from 5 to up to the maximum of 7.5. But there is some preference of this fault producing earthquakes that are between 7 and 7.5. And then you have like the pure characteristic model that is this green distribution, and that will tell you that that fault is only producing earthquakes that are either some magnitude between 7.5, 7 and 7.5, with the highest preference around the mean. And so essentially, what model we choose, we make different assumptions about the behavior of a particular fault. And the last case that you can have is using this or any other shape that it is integrating to one. You can have a composite model that we will see next. Like can have this characteristic shape, then another tail, and it can be as complicated as we want to be, as long as we have enough data to constrain that geometry. So the density function for the truncated model is this one, which I believe we see. And so this is the exponential decay as the magnitude is increasing. And we have this normalized term so that the area of the density function integrates to 1. And if you were to look to observe earthquakes from afar, so if you were to describe the seismicity of the entire Earth, or maybe of a continent, or of a state, or maybe even like a large amount of land, you will see this relationship showing up in the observed seismicity. So that's why sort of this was the first one that was proposed. But if you start observing individual faults in terms of seismicity, you will see that this relationship is falling apart. And this brings us to like sort of the notions of the characteristic magnitude and the characteristics-based magnitude models. So here, this is a relationship that shows the cumulative number of earthquakes exceeding some magnitude. So how many earthquakes of a magnitude 3 and above you can have. And these are the data points that are collected. Based on, so you can have some data points that you can collect based on observed seismicity. So you have like your seismometers, you detect earthquakes, you define the magnitude, and then you see how many you have. But then you can also do like trenching or through like geological data, calculate back what is also the rate of the earthquake. And you see there is some discrepancy. And the reason for that is, if you remember, I think back to the first lecture of like the notion of like the button of the zipper for the large earthquake, once you start pulling out a zipper, there is no reason to stop at a particular point. You will stop when you have like some barrier. And these barriers are typically at the end of the fault. So if your rupture starts growing and growing and growing, it will not stop on its own. It will only stop because it reached the ends of that particular fault and arrests it. So that's why, like, if you start having like large earthquakes, then there will most likely it will be as big as the fault can accommodate until the rupture is arrested at the boundaries of the fault. And one of the models that tries to describe this behavior is the characteristic magnitude model or the Janssen-Coppersmith magnitude model. And so this has this exponential decay for the density function as a function of magnitude, but then there is a higher chance of producing a characteristic magnitude event. And this is the standard form that describes this, but you can also change this depending on how wide you want to have this region or how tall you want to have this part relative to the rest. So in its standard form, this has a 0.5 units of magnitude, 0.25 magnitude units either side from the characteristic. And then the rate for the characteristic magnitude, like you assume that you will have as many characteristic magnitudes as M characteristic minus 1. And that's for this preference. Or another model that is even more strict in this sense of like a characteristic type style magnitude is the pure characteristic magnitude, which is simply like if this is car is like a truncated normal distribution that you assume will only go as any number of standard deviations away from your characteristic magnitude. And again, like this is the density function of our normal distribution, and you have this normalized term so that like to account for all the area that you lost on either tail, so that the remaining area still integrates to one, and it is a valid density function to use. And the last type of model that more and more you will see nowadays, especially in areas where you know the seismicity more well, is composite model. So here is one model that has been proposed in the past that has an exponential decay. Then around the characteristic magnitude it has this truncated bell shape. But then because like people are unhappy with sharp boundaries, they say, and what if you have a magnitude 7.55 instead of 7.5 or 7.6? They introduced this second exponential decay that decays even faster and can go to as large magnitude as you want, or a magnitude that is so rare of being exceeded that you can now truncate your distribution more confidently. Or there is like in California, you will see the U-surf model, and that's like the entire state seismicity model. And for it, based on GPS stations around the state, they try to come up with the magnitude recurrence relationship for every possible fault. So for example, here you have the San Andreas fault and all the possible segments that can be combined in creating that rupture. And this is all the alternative models that give you the magnitude relationship for all the possible segmentations. Any questions on the magnitude models? Okay. So up to this point, we described the shape. Now we need to come up with a rate. There are three approaches. Again, depending on what information you have, there is the historical seismicity approach. So either like through like historical records or instrumented history, where you use your instruments to define the size of the earthquakes. You see what is the seismicity in the past, and you make the assumption that the same seismicity applies to the future. It can be based on geologic information. So from introductory classes in geology, I'm not sure if you covered like trenching, but like you essentially excavate the earth, and as you go deeper, you go into the past. And if you see like discontinuities there, that can indicate a fault, and you date when these discontinuities happen, and that gives you some long-term slip rates. Or based on geodetic information, and that goes back to balancing the moment magnitude. So if you are here and you know how much each side of the fault is moving relative to the other, you can calculate the slip rate and make sure that the energy that will be released by your magnitude recurrence relationship will balance the seismic moment that is accumulated based on the slip rate that you have. Because around here and in most places, typically the information to have available is historical seismicity, then I want to go over the magnitude completeness, which is what you need to consider when you define the seismicity based on that. So to have a sense of how often you have earthquakes based on historical records, the assumption there is that your historical records have recorded all the earthquakes that had happened. And as you go back, that's not always the case. So, like for major earthquakes, magnitude sevens, like even depending on which region you are studying, you can have records that go back to thousands of years, but for a magnitude 3 or a magnitude 4, no one will write down in their notebooks that, oh, a magnitude 4 happened because it's nothing special. So for those, typically it's only the part of the record that is based on instrumented seismicity. And so the challenge is now, how do we define for each magnitude value? We have a historical record. So this is for the seismic study that I showed in the beginning of the class for the case of Philippines. So here, what we calculated and plotting is the annual frequency of each magnitude beam. So this is the annual frequency for earthquakes between 8 and 8.5, 7.5 to 7.9, and so on. So the way that you empirically calculate the annual frequency is starting from the present, you go back, you count how many earthquakes you have in your catalog, and then you divide the number of earthquakes by the period length. So, and what you can see for all these beams is that you have a part of this curve that is more or less flat, so the annual frequency doesn't change, and after some period where the annual frequency starts decaying. And there is no natural reason where you as you go further and further into the past, you stop seeing that many. This will be magnitude 5.5 to 5.9. The only reason that you have this decay is because your catalog stops being complete. So based on where this curve is flattening out is one way to define the completeness of your catalog for each magnitude beam and calculate the rate for that magnitude beam only looking at earthquakes that happen, like in this case, in the past 20 years. Is this concept clear or no? Silence means two things. Everything is clear or everything is confusing. Good, George?
I say 50-50.
Okay, what is confusing?
I think that this part is, I feel like, pretty clear. I think I got kind of confused with like the hazard like integration
Okay.
part. But that was something I was just gonna, I felt like I could go back to and then just like on my own.
Okay, yeah, and if it remains confusing, then we may revisit it again to, like repetition typically helps with understanding some material because the second time we see it, say, oh, it makes sense actually. Anyone else maybe on this particular part of the lecture that is confused? Yes, please.
A bit like name question, but like the observed period isn't the reciprocal of observed period the annual frequency.
So this and this being the reciprocal of each other,
Yeah.
how do you define annual frequency?
It's like the reciprocal of the period.
It's not. Those will be the reciprocal, so it will follow a one-to-one line if you had only one observation, right? Because your annual frequency is the sum of earthquakes from magnitude like I to I plus 1 divided by the observed period. Right? So if you have like so this more or less okay, so this is 10, this is 1000, so 100 it should be somewhere here. So this is 1/100 because you had observed only one earthquake that is below magnitude 8, and that's why your annual frequency is 0.01. Is this helping the relationship? Yeah. Any other questions? And so in choosing this, it can either be based on the catalog itself or based on some knowledge about the instrumentation around the area that you study. And so the worldwide seismic station network was developed back in the 60s for a different reason, not to detect earthquakes. But essentially, since 1967, more or less you can feel comfortable that you can record any magnitude 7, any magnitude 4 around the world. And here is for a study that I'm doing in Turkey. And here we are plotting sort of the magnitude in the catalog versus the time. So you have like from the 1900s up to 2026. And you see that like, I don't know, before 1960s, you are only recording earthquakes that are above magnitude 5.5. And that's because these are larger earthquakes. And so even if you don't have like a station very close, you will still be able to detect it. But as you go through like the 1960s and then the 1970s and the 1980s, you see that you all of a sudden have in your catalog magnitude 5s and 4.5s and even smaller. And that's not because these earthquakes didn't happen before, it's simply because we didn't detect them before. So that can also be like this date or other information about the local seismic stations can help you decide what is the appropriate completeness period for its magnitude being. Maybe the last thing to define for the maximum magnitude is for the magnitude recurrence relationship is here. So how long should it extend? And that has also changed as our understanding of earthquakes is evolving over the years. First of all, what should be the maximum magnitude? Is it really we call it maximum, but is it truly the maximum possible earthquake? Or actually, I'm giving the answer. But essentially, all of these processes are unbounded in terms of their upper limit. Like, if you tell me, like, there is a possibility that the entire San Andreas fault will connect and will start, I don't know, from Seattle and rupture until Los Angeles, and that will produce like a magnitude 8.5. Is this possible? The answer is yes. Is this likely? The answer is extremely, extremely low. So the maximum magnitude here, you can think of it more of like a practical definition of what is meaningfully, like what is a large magnitude within a relevant time frame that is relevant for the hazard analysis that we calculate, because we can extend these relationships further and further to larger magnitude, but because those earthquakes will be so rare, the chance of them happening, if they were to happen, they will have a catastrophic consequences, but the chance of them happening is so small that for the next 500 years that you only care about, most likely they're not going to happen. And how we define this maximum magnitude has changed over the years. So maybe in the 70s, you will identify a fault and then you will say, okay, this fault, maybe 1/3 or half of it will rupture within during one earthquake. And so they will take the area of half of the fault or 1/3 of the fault, and from the area back, calculate what is the magnitude and define this as the maximum. In the 80s, where we started like understanding that there are boundaries in the fault that may arrest the rupture, then you will define the maximum magnitude based on where these sort of constraints in the fault may locate, and assume that the area within two constraints is the one that will um, that will rupture on its entirety during an earthquake. And then more recently, we account for the segmentation. And so this is the idea that you have all these different segments, but if the earthquake and sort of the speed of the rupture is high enough, then the rupture can propagate to the following to the following segment. And for example, this is the earthquake from 2023 in Turkey. So the earthquake actually started on this small segment, and we like people would say because of this very sharp angle, most likely it would have been arrested here. But in this particular case, the rupture propagated to this segment boundary, but and then continued on either way of the rupture. And so in the new models, we now have alternative branches in our model accounting for all possible segmentation. So what if this segment ruptures on itself, or what if this connects with the remaining ones, and then what is the likelihood of that happening? And then now, so what you will do is you will have all these possible segmentation scenarios, calculate the entire area of the segment, and from that calculate what is the corresponding maximum magnitude that segmentation can produce. Questions on this? Okay. So this will go back to I think we covered moment, how to balance the moment on a previous lecture in terms of theory. So I put an example here, and that's one of the things. So this will be for a simple case, but this will be part of the homework that I will give you. So maybe we can go through that for this simple case, so that then you can figure out how to generalize it. So let's assume that you have a hole, and we know its length, the width, and the slip rate. And here, because we want to like a simple model, we will assume that this fault is capable of producing only one earthquake, or one phase earthquake, and that size earthquake is the characteristic. So how do we estimate the magnitude of the characteristic earthquake? I think in lecture 2 we saw the relationship that M is log base 10 of the area +4 or approximately +4, and this is in kilometers squared. So we know the length, we know the width, the product of these two is the area. We plug it into this relationship, and this gives us the characteristic magnitude. Who can tell me what to do next? Anyone? That's the end goal. So here is the annual frequency of exceedance. or the analog frequency because it's only one magnitude, we are here. So what is the remaining steps? This is the moment magnitude, right? What can we do from the moment? Like, how did we define moment magnitude? It's in the name. Based on the seismic moment itself, right? Okay, so we can calculate what is the moment rate, so how fast seismic moment is accumulating based on the dimensions of the fault and the slip rate. And the way that we do it is we take the area of the fault in squared centimeters times the slip rate in square centimeters times the stiffness, which typically you can assume a value that is equal or around 3 times 10 to the power of 11 times per centimeter squared. And that tells us how much seismic moment is accumulating over 1 year, right? From the moment magnitude, we can now calculate what is the seismic moment that is released by this earthquake. So if you remember the relationship that we had, come on. MW is 2/3 log of M naught plus 10.7. And so if we know this one, we can calculate what is the seismic moment. And so solving for the seismic moment, it's 10 to the power of 1.5 times, this is 2/3 times 7.18, where did this came from? The characteristic magnitude, and 3/3 times 10.7, and that is the amount of seismic moment that will be released by this earthquake if it was to happen. So on average, we'll have one earthquake every time that we accumulate this amount of energy. So the moment rate divided by the seismic moment released by this earthquake will give us how many earthquakes per year we're going to have. It's a unit of force. In seismology, it's simply something to memorize, if that helps you. This is like, I don't know, imperial units of force that have been traditionally used when the seismic moment was defined. Yeah, but if you know, like, this relationship will give you the seismic moment in times, and if you use the stiffness as 3 times 10 to the power of 11, then that will cancel out. That's what I have for today. Maybe one question from my side, like, how is the progress of the class going? Or are there any questions or anything to adjust? Okay. Good, I will assume. Any questions from today's lecture? Then that's it for today. So I will release the homework. I don't know if today, but I will try before the weekend, and then maybe on Monday we can also discuss it. But if you have a moment to go over it over the weekend, I think will help to have a more productive discussion and then move with the next material.